In this video, we are going to talk about the volume integral operator that you see here. This is our overview slide, which we'll really spend maybe like 3 minutes on. It's very short. Before we do a bunch of examples, because I feel like to get the hang of doing volume integrals, it's just important to see a lot of examples. But before we do examples of volume integrals, we're going to look at the volume integral operator itself. That is the integral of over V over volume d tau. And then after we look at the operator itself, we'll look at the volume integral as applied to a scalar field. So that's the integral of the volume d tau operating on phi, where phi is a scalar field that maps from R3 into R, or potentially from R3 into R. But it always maps to the scalar fields. And then what else do we have? When we do this volume integral, we always produce a scalar representing the volume of V. In Cartesian coordinates, we have another kind of way of writing this. And then the majority of the rest of the video is doing some examples. The first one is deriving the formula for the volume of a sphere radius 1, and we verify that it's equal to 4/3 pi. In this case, we have our parameterization of our unit ball, and because we're just finding the volume, we integrate phi equals 1. There are a couple of other examples we do where we just set up the integral. But the last one includes a phi that is not simply equal to 1, but it's a phi that is a mass density. And so we find the mass of the object by integrating the mass density over the volume. We start with talking about the volume integral operator, and there's not much to say except that this is what it looks like. The symbol is integral over V of volume, d tau, where d tau is the differential volume, and V is the total volume of integration. The second thing we'll talk about is the volume integral of a scalar field. So we'll apply this volume integral operator on phi, where phi is a scalar field. In other words, it maps from R3 to R. And the first thing to note is that this volume integral produces a scalar representing the volume of V. And also we could write this in our Cartesian coordinates with using index here, where we have dx1, that's integral with respect to our first variable, often we call that x, dx2, that's integral with respect to our second variable, that's y, and dx3, that's integral with respect to our last variable, third variable, which is z. So this volume integral is a triple integral. One thing to mention, when we did double integrals in vector calculus, that is when we integrated over a two-dimensional domain, like here we integrate for some values of x and values of y, and they give us this shaded region, which is the domain. When we integrated some function z of f of x, y, that is for every point x and y in the domain, we could get a height, and then that results in some surface that's hovering over the domain. When we integrated our function f of x, y with respect to y and x, our result is we would get the volume of this solid here. So now when we have a triple integral for our volume integral, we're integrating with respect to dx1, dx2, and dx3. Our domain is a volume, and the result will be a four-dimensional hypervolume. So unlike double integrals, we can draw this volume. When we do triple integrals, we often draw the domain, and we neglect to draw the four-dimensional hypervolume for hopefully obvious reasons. Our first example is to derive the formula for the volume of a ball. So we're integrating over a volume d tau equals 4/3 pi, where V is the unit ball given by the equation x squared plus y squared plus z squared is less than or equal to 1. Over here, I have a drawing of our ball or our sphere, and its radius is equal to 1, and I have that z is related to x and y by z is the square root. Positive is the upper half of the sphere. The bottom is the lower hemisphere. So the positive is z is equal to square root of 1 minus x squared minus y squared. And I really should have put a plus or minus here. In the xy plane, where z is equal to 0, we see that y is related to x as square root of 1 minus x squared. And again, that should be plus or minus. In this example, we're going to integrate our function 1. So our scalar function in this case, our phi, is equal to 1 because that's how we will get the volume. When we look at our limits of integration, first, you can choose this to do in any order, and especially in this sphere, it's all symmetric. But generally, I like to do dz first, and I like to write z as a function of x and y. As I had mentioned, z, this top half of the hemisphere, is equal to the square root of 1 minus x squared minus y. The bottom half of the hemisphere is equal to negative square root of 1 minus negative square root of 1 minus x squared minus y. So these are our limits of integration. In other words, in the z, and the height, when we talk about height, we're going from the bottom of this curve, which is given by z equals minus 1 over 1 minus square root x squared minus y squared. So we're going from the bottom of this curve to the top of this curve. When we're over here, we're still going from the bottom of this curve to the top of this curve. So we're integrating over the height z. Once I integrate over the height z, I have to think about y and x. And I don't know why, I favor x at the end, but I'll look then at how y depends on x. And to look at how y depends on x, I set z equal to 0, and I see that y is equal to plus or minus square root of 1 minus x squared. You know, the positive y being plus and the negative being negative. So here I have my limits for y. And again, the idea is when z is equal to 0, we have this equation of a circle for this is our x, y plane, actually I should do it this way, our x, y plane. So here we have y is equal to positive square root 1 minus x squared. Down here we have the curve y is equal to minus square root of minus x squared. So when we integrate y, we're basically going from the bottom of this curve to the top of this curve. And this way we'll get all the y variables. So that's what this part here is with respect to y. And then finally, when we get to x, looking at z equals 0 still, we have that x over here goes from negative 1 to 1. And that will, letting x go from negative 1 to 1, y go from negative square root of 1 minus x squared, positive 1 minus x squared, we will get this entire circle. When I do this inner integral dz, I'm going to have my limits of integration here, but integrating 1 with respect to z, I get z, and I plug in my limits of integration, so I'm going to get 2, because this is, double this, and I went ahead and pulled it on the outside, my limits of integration, square root of 1 minus x squared minus y squared dy dx. There are two notes I would like to make here. The first one is when I integrate with respect to z and I plug in my limits of integration, my z variable disappears. So when I integrate with respect to z, I have done what we call integrated out my variable z. And that happens again because I integrate with respect to z, so I have some function with respect to z, and then I plug in my limits of integration, but at this point, my limits of integration are z written in terms of x and y. So that is how I have z is integrated out. In your book, and I really should embrace this, I should really stick to this notation where I put this part of the dx1, dx2, dx3 as part of the integral operator. However, because I am I like being able to see, okay, first I'm integrating with respect to z, then I'm integrating with respect to y, and then I'm integrating with respect to x. I guess I really can get used to this. I just have to get used to saying, first I'm integrating with respect to x, then with y, then with z, but I'm just so used to this notation that I kind of stick with it. But really, I can rewrite this integral in this form, and then just know I need to work from dz, dy, dx. You can let me know if you'd like in the comment if you think that I should be using this notation, the integral operator notation, more in my integrals. To perform this integral with respect to y, I looked this up in my integration table. So if I have the square root of a squared minus x squared dx, then the integral is x over 2 square root of a squared minus x squared plus a squared over 2 arc sine of x over a. So here I'm going to let this portion, my 1 minus x squared, equal to a squared, and then I'm going to let my y squared equal to the x squared in this formula. So let me just put this is my a squared, and the y squared plays the role of x squared. And so now I bring out my 2. I have my limit of integration, -1 to 1, that stays, but I'm integrating this. So I have x over 2. Remember, my x is equal to y. That sounds funny, but yeah, so it's y over 2, square root, and then I have my a squared minus x squared again, plus a squared is 1 minus x squared over 2, and then arc sine of x, which is y, over a, which is square root of 1 minus x squared. And I plug in my limits of integration. Now, plugging in my limits of integration for y, because we just integrated with respect to y, I have my 2 minus 1 to 1 y, then I'm going to plug in my square root of 1 minus x squared over 2, square root of 1 minus x minus y squared. Plugging in this squared would give me 1 minus x squared, so this cancels and it goes to 0. Here I have 1 minus x squared over 2 arc sine of y, which is square root of 1 minus x squared over square root of 1 minus x squared, so this is arc sine of 1, minus, and then I'm going to plug in this limit of integration. In here, this is going to go to 0, and then over here I'll have 1 minus x squared over 2 arc sine of minus square root of 1 minus x squared over square root of 1 minus x squared. So these are the two terms I have left, and I'm integrating with respect to x. And here I have the rest of my calculations, and you can see then for volume of a unit sphere, I get 4/3 pi, which is exactly what I would like it to be or expect it to be. This problem will go faster because we're only going to set up the integral. We're not actually going to do the integration. So set up the integral to find the volume of the solid region bound by the hemisphere x squared plus y squared plus z squared equals 4 when z is less than or equal to 0. And the paraboloid z equals 4 minus x squared minus y squared. The first thing I want to do is know what this region, the solid region, looks like. So I know what a hemisphere of radius 2 equals or looks like. So let's look a moment at this paraboloid. Z equals 4 minus x squared minus y squared. And one thing we can look at is kind of compare this equation, this paraboloid. We're kind of given a hint, it's a paraboloid. So let's look at this paraboloid, z equals x squared minus y squared. Then after we have this, we'll look and see what happens when we have the negative in front of it, and then when we add the 4. So let's consider this paraboloid, z equals x squared plus y squared. And if you recall, to help us graph in 3 dimensions, we often look at level curves. That is, we look at what happens when we hold z, the height, constant. So when we're at a height of 0, our x and y are also 0. So we get this single point here. When we're at a height of 1, you can see that our level curve is going to be a circle of radius 1. When we're at a height of z equals 4, you can see that this equation gives us a circle of radius 2, and a height at 9 gives us a circle of radius 3. So this is kind of it's sort of like a topographical map. We actually discussed this in an earlier video. So you can think of then raising each of these level curves to the height of z. So when z is 0, we get the singular point. When z is equal to 1, so at height z equals 1, what's happening with this curve is we get this circle of radius 1. When we're at height z equals 4, we get this circle of radius 2, and when we're at height z equals 9, we get this circle of radius 3. So essentially what we're doing is we're stacking up ever increasing circles. So what that gives us is this looking paraboloid here. But our curve is z equals 4 minus x squared minus y squared. So this negative here has the effect of turning this bowl upside down, and then we're starting at the single point 4. So you can also kind of, if you like, you can kind of do level curves, but intuitively this is what's happening. It's turning the bowl upside down, starting at z equals 4. Now I need to put my two shapes together. So on top, when z is greater than 1, I have the paraboloid. So that's this paraboloid on top, my bowl. But when z is less than 0, I have this hemisphere. So I labeled my paraboloid here, my hemisphere here, and then also this circle where the hemisphere and the paraboloid intersect. That's at z equals 0, right? Because it changes at z equals 0. So at z equals 0, when you plug in z equals 0 here and z equals 0 here, what you get is a circle of radius 2. So this is x squared plus y squared equals 4. And now I'm ready to get my limits of integration. And often I like to do x last, and you can see it's actually kind of easy in this picture that x is going from negative 2 to 2. Now we look at how y depends on x. And so we look at z equals 0, and we get our equation that we have this equation of a circle of radius 2. So y is going to be equal to plus or minus square root of 4 minus x squared. So that's my next set of limits. And then my z, you can see I go from this bottom curve here. So that's solving for z. Z is going to be the square root of 4 minus x squared minus y squared, which I have here on the bottom. And at the top, we're going to get z equals 4 minus x squared minus y squared. And then since we're finding the volume, we just have our function, our phi is just going to be 1. I like this next example because we actually have a function phi other than 1 now that we're going to plug in. Remember, it's a scalar function. It takes 3 variables, x, y, and z, and maps it to a single real number. I guess it could be complex, but in this case, it's a real number. So the example, let V denote the solid tetrahedron with the vertices at 0, 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And this is my drawing of this, my lovely drawing of this tetrahedron. So suppose the mass density inside the tetrahedron varies as f of x, y, z equals 1 plus x times y. Find the total mass of the tetrahedron. So what we're going to do is this, we're going to integrate this density over the volume, which is why we have the volume integral. But before we integrate, we need something more than just the points of this tetrahedron. So we do need, first, we do know that the back wall of this tetrahedron is the y equals 0 plane. Is that right? Yeah. The back wall of this tetrahedron back here is the x equals 0 plane, and then here we have the z equals 0 plane, but we do need an equation for this, this plane over here. So this is the equation of the plane which contains the points 1, 0, 0, 0, 1, 0, and 0, 0, 1. And for that, we're going to dig through our vector calculus book. It's probably towards the beginning of your vector calculus book, how to find the equation of a plane containing 3 points. Well, the first thing we're going to do is we're going to use these 3 points to make 2 lines in the plane. So I'm going to use this as kind of my anchor, and I'm going to use my 1, 0, 0 minus 0, 0, 1, and then I'm going to subtract 0, 1, 0 minus 0, 0, 1. And so these are 2 line segments in the plane, my 1, 0, 0 minus 0, 0, 1, and 0, 1, 0 minus 0, 0, 1. These are 2 line segments in the plane, and when I cross them, I'm going to get a vector that's perpendicular to both of these lines. That's the nature of the cross product. So in fact, I'm going to get a vector normal to the plane because these 2 lines lie in the plane. Also, it's important that these 2, the vertice you subtract is the same vertice in each case. Anyway, so I take the cross product of this vector minus this vector, so I get the cross product of 1, 0, minus 1. This 0, 1, 0 minus 0, 0, 1 gives me 0, 0, 1 minus 1. I take the cross product and I get the normal vector as 1, 1, 1. And this is going to be useful in a minute. The next thing I'm going to do is I'm going to let x, y, z be a point on the plane. Then x, y, z minus another point on the plane, and you could choose any of these 3 points. I chose 1, 0, 0, so I have x minus 1, y, and z. Now this is another line segment on the plane. And because n is normal to the plane, the normal dotted with this line segment, which is equal to my normals 1, 1, 1, dotted with x minus 1, y, z, should equal to 0. And from there, I just do the dot product, I do some algebra, and I get x plus y plus z equals 1 is the equation of the plane. And now I'm set up with this picture to figure out what my limits of integration are. So I start with x. X is going to go from 0 to 1. Y, so it would be a mistake to say y goes from 0 to 1 because then you get this whole square, right? Really what y does, once you have a value for x, y then, y is how much we go along in this direction. Y goes from 0 up to this line here. I guess this line, I'm going to outline it in green, right? So here is another point of x. It's going from 0 up to the green line so that it makes the triangle. So this triangle here, I need the equation for this line here. If I just kind of take this out so I can only look at it in 2 dimensions, my x and my y, so x and y both are bounded by 1. So the equation of this green line here is simply y equals minus x plus 1. So my limits then are going to go from 0, as we said, over to the green line, which is 1 minus x. Then finally, I have this, the z goes from 0 up to this plane here. So 0 up to 1 minus y minus x. And then I integrate my density, which is 1 plus x times y, and then I integrate with respect to z, y, and dx. And I did not do all this integration for you. It's actually a lot of algebra, but the final answer I believe is 7 over 40. To review what we covered in this video, we looked at the volume integral operator, which looks like this, or this is how we notate it, the integral of over v of volume d tau. We then looked at applying this operator to a scalar vector field. So we have our volume integrator operating on phi, where phi is a scalar field. It maps from R3 to R. And the first thing to note about this volume integral over a scalar field is that it produces a scalar representing the volume of v. Then next we did several examples. The first one is deriving the formula for the volume of a ball or a sphere. And we confirmed that it's equal to 4/3 pi, where v is the unit ball, x squared plus y squared plus z squared, less than or equal to 1. And also whenever we want to know the volume of, if that's all we want to do, then we just plug in phi equals 1. We did have an example of a phi that was equal to a function. Actually, it was equal to a mass density of an object. And then we found the mass of the object by integrating the mass density over the volume. So that's it for this video. Thank you for watching.